If you've ever ordered something from the internet, you would know it typically comes in a rectangular box. But what would happen if quadrilaterals were not an option? Let's say you're moving into your first apartment and you have oddly shaped things to pack, like your favorite lamp, your comfy couch, your tables and chairs, and of course your mother's dishes. What kind of package could you put them in? So we begin to experiment with what other shapes can fit in boxes and what other types of boxes would be useful.
Let's simplify our application a bit. First, we'll pretend our packages are two-dimensional. Second, all of our shapes are either circles or regular polygons, which we define as a polygon where every side is equal length and every angle is equal. We define the polygon as being inscribed if all of its corners touch the outline of the outer shape. The outer shape is then circumscribed around that polygon. Circles are inscribed when it is tangent to every side of the circumscribed shape.
As we begin to look at easily inscribable shapes, we discover that any regular polygon can be inscribed in another regular polygon with the same number of sides. The inscribed shape could lay on top of the outline or can be drawn by connecting the midpoints of each side. So for example, we can take an octagon, draw all the sides, locate the midpoints, and then connect them. And there you go. You now have an octagon inscribed in an octagon. This method can be applied to any regular polygon. We are also interested in rotations. Specifically, how many places can you put a certain corner of the inner shape onto the outer shape? As shown in the image, corner A can be rotated 6 times. In these situations, it is easy to see that any given corner can be rotated to each corner and midpoint of the outer shape that we have 2 and unique rotations. Next, we wanted to look at inscribing different regular polygons and seeing if there were any unexpected patterns. One of our most interesting findings was being able to perfectly inscribe any 2 angon in an angon. Anyone can try this. The first step is to draw your favorite regular polygon. Next, you need to draw in-line segments to mark the corners off. But you can't draw these lines just anywhere on the sides. The triangles that are formed in the corners must be congruent isosceles triangles, or else the inner shape is not necessarily a regular polygon. The side length of these triangles can be calculated using trigonometry and substitution. Then when you repeat this process with other polygons, you will notice that the inscribed shapes look more and more like circles, which we will discuss later. As far as we can tell, there is no possibility of inscribing anything larger than a 2 angon, but it remains to be proven that anything within or fewer sides can be inscribed into said angon. Determining some of the patterns that can be found while inscribing has been made difficult due to 2 anomalies, the triangle and the square. As we have played around with what shapes fit inside each other, we consistently find that the triangle and the square can fit into any shape we put them in. Triangles and squares are relatively easy to inscribe in another shape, simply because there are only 3 or 4 points you have to place on the outer polygon. This series of images illustrates the phenomenon we've discovered.
This discovery about triangles and squares has led to a debate. It appears that, by this evidence and some fiddling around in GeoGebra, that any polygon of size less than n can be inscribed in an n-gon. There is some dissent, however, and it remains unproven. Trying to generate a method for inscribing an arbitrary regular polygon into some other polygon has proved challenging in general. The most successful method we found involves inscribing polygons into circles and circles into polygons. This leads us to a theorem. Every regular polygon has an inscribed and a circumscribed circle. To prove that, take a regular polygon with n sides. We can draw triangles by bisecting the polygon's angles and continuing each line segment until we reach the opposite edge. This will give us either n if n is even or 2n if n is odd isosceles triangles. Because the polygon is regular and we've bisected the angles, the triangles are all congruent by angle side angle. Using the side of the triangle that is not shared with the polygon as the radius, I can draw the circumcircle around it, inscribing the polygon in a circle. The inscribed circle follows similarly, but with the radius as the distance between the midpoint of each side and the center point. By using this method, we can pack any regularly shaped package into a circular box. Circular boxes are not easy to work with, however, so we can put each circular box into any other regularly shaped box we want. While this is not a perfect solution, it is easily generalizable. We can actually calculate how much space we waste with this method. Using a very similar process as before, we found the area of a regular polygon with n sides as a sub n equals 1/2 n r squared times the sine of 360 degrees over n, where r is the radius of the circumcircle. Taking the limit of this as n goes to infinity gives us a equals pi r squared, which is conveniently the area of the circumcircle. This means that inscribing polygons into circles becomes more space efficient as the side number increases, which makes sense. It also means that inscribing circles into polygons wastes less space as the number of sides of the circumpolygon increases. To continue our investigation, we would find proof or a counterexample to polygons with fewer than n sides being inscribed in an n-gon. We can also extend our inquiry to three-dimensional objects such as cubes and spheres. We can also explore how to fit multiple shapes in boxes or how non-regular polygons can be inscribed. We hope this presentation has been enlightening.
This didn't work out right. This didn't work out right. You seen this? Look at that. That's not right. That's not right.
That's not right.